Okay, so here's where we were last time. We were talking about the chain. Oh yeah, thank you. We were talking about the chain rule. Here's sort of an expanded form of the original version of the chain rule that we wrote down, which is that there's a simple multiplicative relationship between Jacobian matrices. So the Jacobian matrix for the composition is the product of the individual Jacobian matrices. So that looks a lot easier when you write it down like this, right? But if you want to expand that whole thing out, this is how you're going to be dealing with it if you're using it. So it's bigger and uglier. So interestingly, if you focus your attention on a single entry in that composition Jacobian matrix, what you find is that it's as an entry in a product of two matrices. It's the corresponding row of the left matrix. You'll see those entries here. Dotted with the corresponding column of the right matrix, and that's those entries here. So just using what we already know about how to multiply matrices, we get an alternative form of the chain rule. So instead of writing it as a matrix product, you can write the chain rule one variable at a time, or one partial derivative at a time. So one output variable with respect to one input variable at a time, as this dot product. It's still kind of a complicated, ugly-looking formula, right? But certainly not as bad as this monstrosity up here. Okay. So what I want to do now is give you a motivation for sort of a plausibility point of view on that new version that we're looking at here. Why is this natural? How should you think about this formula? And I'm going to introduce the idea of intermediate variables. So specifically, the y variables here are what I'm going to call intermediate between the xj variable that we're taking the derivative with respect to, and the zi variable that we're taking the partial derivative of. Okay, and the idea of intermediate is as follows. If you were to change xj just a little bit. Let's suppose you have some values for all the variables, and everything's going to stay constant. We're just going to tweak xj just a teeny tiny little amount. Well, what happens? Well, if you change xj a little bit, then that change is going to sort of propagate. In other words, that change in xj is going to cause all the y variables to change some small amount, because all of these y variables are functions of all of the x variables, including that xj. Okay, now, so what? The thing is that each one of these y variables, when it changes a little bit, that's going to cause a change in zi. Why? Because zi, like all the other z variables, is a function of the y variables, right? So you change y1 a little bit, that's going to change zi some little bit. Okay, so what I mean by propagation of changes is that when you change xj by some amount, those xj changes are going to cause changes to these variables. Those changes are then going to propagate along and cause changes to zi. All right. Now, what does that have to do with the above formula? This is why we call them intermediate variables. It's because they're sort of their changes are an intermediate stage between xj changes and zi changes. Fine. But where does that formula come in, and how does that relate? Well, what I'm going to do is I'm going to look one at a time at all of the sort of possible propagation paths that those changes might take. So in other words, the changes that xj eventually causes in zi get there by, one of m different possible routes. In this case, here's the first one. An xj change could propagate through y1 and cause a zi change. How would we sort of keep track of the proportion? What's the proportion between how much change was here and how much of that propagated through y1 to cause a change there? Well, the factor that relates those two changes is a product of two individual factors. There's the factor of, how much does an xj change cause a y1 change. So xj causes a y1 change, and that partial derivative is the factor that relates those changes. And then the y1 change is going to cause a good color, red, I guess, I don't know, a zi change, and that factor is that partial derivative. All right, so in this equation up here, this first term in particular, that first term is the product of these two factors, each of which is a factor in sort of the total factor of how much you multiply by an xj change to get a zi change along that path. Does that make sense? Everybody happy? Okay. So I think it's interesting how in this equation, each, analogously for the other terms, by the way, but so then each term corresponds to a propagation path. In each term, each factor corresponds to one of these individual steps of propagation of these changes. And so each of the factors in each of the terms of that equation relates to something in this diagram. Okay. So analogously, let's see what would be a good color choice. Oh, well, I've used all the colors at this point. Analogously, this relates to that factor, and this relates to that factor. And so this term relates to the total factor along that propagation path. Okay. All right. So that's a nice way to think about this formula. If you're looking for a sort of a way to remember this formula, for example, I think a pretty good way to remember it is to think about, okay, well, what are the various intermediate variables? Let me use a better color choice. What are the various intermediate variables? And notice that all those intermediate variables show up in this way in terms that relate xj changes to zi changes. Very happy? All right. Okay, so I'll show you an example. So I'm going to look back at the previous example. In this previous example that we did, I gave you explicit Jacobian matrices, and the question, we asked, how can we write down sort of the composition Jacobian matrix, and then eventually, in the end, what was that individual partial derivative. So I'm going to compute now this individual partial derivative, not by multiplying the whole Jacobian matrices, not that there was anything really wrong with that. I mean, this calculation is pretty straightforward, right? But let's see how the calculation would look different if I used this intermediate variable point of view. And so the intermediate variable point of view says that, look, well, in trying to compute this partial derivative, we've got the G3 variable that we're taking the partial of, and we've got the X1 variable that we're taking its partial with respect to. Right? And what are the intermediate variables between X1 and G3? Well, between that input variable and that output variable, there are 3 intermediate variables, which we decided to call Y1, Y2, and Y3. So, Y1, Y2, and Y3. So this formula then for the partial derivative that I'm trying to compute just comes from looking at the statement of the question, identifying which input variable, which output variable, and what are the intermediate variables in between them. It's a question of looking at the diagram, relating all the different functions and variables involved, and seeing what connects to what, in what ways. Right, so then now how would I solve the problem? Where does the answer come from? Well, I realize one at a time that these entries, as they are partial derivatives, are entries in one of the given Jacobian matrices. Now, which entries are these in which of the given Jacobian matrices? Well, I'm looking at partials of the G variables with respect to the Y variables, so that's going to be entries in this matrix. Let me erase this. Specifically, now you'll notice that I'm looking at partial derivatives. These circled partials are partial derivatives of G3 with respect to the various different input variables, Y1, Y2, Y3. So that means that we're looking at the third row. G3, specific output variable. So we're looking at the partial derivatives that are in the third row of that matrix. So these are the numbers in question, 0, 1, and 0. And you'll notice those go here. So 0, 1, 0. Right, now what about these partials? These are the partials of, well, all three of the different intermediate variables, but all with respect to x1. Right? So the partials of the intermediate variables with respect to the first input variable. And that means that in this first matrix, we're looking at the first column. So 1, 3, and 5. So 1, 3, and 5. And you'll notice that this is the same answer that we got over here. In fact, not only is it the same answer, it's the same answer by having done effectively the same arithmetic. I mean, if you look at the arithmetic that we end up doing here, these numbers are, where they came from is, well, a certain row dot a certain column, and the row and column in question are this row dot that column. So in fact, not only do we get the same answer, we get the same answer by doing the same arithmetic. Okay. I guess what we've saved ourselves is we've saved ourselves the trouble of doing all of that arithmetic. Right? We didn't really need to compute the other 5 entries of this product Jacobian if, in fact, all we're interested in is that partial derivative. Everybody see what's going on there? So there are different points of view you can take of this. There's a point of view that says that this is a really good way to write down the chain rule. This is, in some sense, a compact, pithy, one at a time, each entry, if you're trying to construct a product Jacobian, if you're trying to compute a partial derivative of variables relating to a composition of functions, and bam, there it is. It tells you exactly what to compute. And that's nice. The disadvantage of that is it's a small scale formula, and there is a very valuable larger scale structure that if you're not, for example, interested in just one variable at a time, just one partial derivative at a time, if you want to understand how the functions, how their full-on derivative transformations relate, the matrix multiplication relationship is extremely valuable. And we're going to see situations where that's huge in a big way. Okay. All right. A very quick little observation I want to make. A lot of you all have probably seen, this is the Leibniz form of the single variable chain rule, and a lot of you have seen this little move here where you cancel the dy's, right? This is actually kind of sketchy. If you cancel the dy's like that, that's suggesting that the dy and the dx are individual values that you are dividing as a fraction. And ultimately, that's actually kind of a problem. These expressions like dy dx, is it really a fraction? And if so, what are these objects? What is dx by itself? What kind of a number is that? What is dy? there are some nasty little problems that go into exactly what these things are. Those problems can be addressed. There are answers, but they're not really addressed very well, very rigorously in most single variable calculus courses. Not that they really should be. It's fairly sophisticated ideas, actually. That's actually a little bit sketchy. And what I want to point out, now of course the result is true. Right? It's not a problem with the result. It's a problem with the argument as it's presented in single variable calculus courses. I want to point out a further argument with that kind of, a further problem with that kind of thinking as it pertains to this. And look what would happen if I apply that same reasoning here. And that is I get a wrong answer. Right? If I take this expression, this sort of intermediate variable, this sort of compactor version of the chain rule, if I were to not use the chain rule correctly, I could argue that, hey, look at this one term. Let's just ignore all of that. Why can't I just do that? Well, you're getting the wrong answer. And part of the reason why you're getting the wrong answer is you're making a wrong argument. Those things just don't just cancel. So be aware of that. I do see this mistake made on a certain fraction of the exams that I grade every year. And importantly and critically, those really don't cancel in a multivariable context. Okay. Right. Okay, so I want to talk about confusion of variables. Before I introduce the multivariable version of this, let me go back to single variable calculus, as you guys know I like to do sometimes. So here's a couple of single variable calculus functions. Easy functions, x squared and x cubed, perfectly innocent functions. I might consider their composition and want to know what the derivative is. Fine, no problem. Okay. Here's a way to seemingly answer that question, and that is to cite a sloppy version of the chain rule. Namely, that the derivative of a composition is the product of the two individual derivatives. And yeah, there's some issue with where you evaluate them or whatever, but the derivative of composition is the product of two derivatives. If you write that down, if you don't think it through, if you don't evaluate correctly, notice that the derivative of this g function, 3x squared, the derivative of the f function, 2x, and you multiply, and that would seem to suggest that the derivative of the composition is 6x cubed. But we know that's wrong. We know the composition is x to the 6th, and the derivative is 6x to the 5th. Okay, so wrong. Right? Now, arguably, the error here is that we didn't evaluate correctly. We wrote down the chain rule sloppily. What we should have written down is this, specifically that g prime, very importantly, is not evaluated at x. It's evaluated at f of x. Right? So I should not have taken the g prime function and just multiplied it. I have to plug in this f of x function, this x squared, into the x here, and we're already kind of unhappy about confusion of variables. I have to plug that into there. Like that. And what we're unhappy about, or what I'm unhappy about anyway, is that I'm letting x equal to x squared, and that's weird. That doesn't feel right. I'm confusing my variables. I've got, in fact, two variables that are really different, and I'm using x for both of them, and that's bad. Okay, so let me show you what I think is a better way to avoid this issue, better than, in this instance anyway, than writing down the chain rule like that and trying to remember what x means in which context, at what point in the equation. Very confusing. Just avoid the confusion of variables. So, same question, same f, same g, composition, want to compute the derivative. Let's rewrite this g function. Let's not write g of x equals x cubed. Let's write g of y equals y cubed. Now that's the same function. It's still the cube function. Whatever you put in, cube it. Right? So, not changing the function. I'm using a different dummy variable, but so what? Right? The advantage to this is then you don't have to worry about confusion of variables. At this point now, I have x is what goes into the f function, and out comes y. And y is what goes into the g function, and out comes, whatever it is that we don't even have to give that variable a name. I guess we'd call it z if we wanted to, but it doesn't really matter. The point is we are no longer using x for both the input of f and also the output of f. So we're not confusing our variables. And at this point, we can be kind of, roughly speaking, as sloppy as we want to be. I can write down the chain rule as derivative of the composition is the product of the individual derivatives. Let's see here. The derivative of f is 2x. The derivative of y, keep in mind that g of y is y cubed, then its derivative is 3y squared. That product is that 6xy squared, and that's not wrong. It's arguably not simplified the way we would like it to be. Arguably, we should take that y, realize that y is f of x. In other words, having done a change of using a different dummy variable, it is keeping track for me. The variable choices are keeping track for me of what's supposed to be evaluated where, and that goes into where y should be, where y is, and correctly puts the x squared there, thus giving me the correct final answer. So this is my preferred point of view on how to avoid evaluating in the wrong place and getting wrong answers due to understandable sloppiness in writing down the chain rule. Don't confuse your variables. Okay. All right. So here's a multivariable version of the same thing. And with that single variable problem in mind, I hope this will make sense. So here's two multivariable functions, and I'm going to look at the composition and compute the Jacobian matrix. Morally the same question. I want to compute the derivative in the form of the derivative matrix of a composition of two functions. And right away, I hope you see the problem, as I have already confused my variables. Right? I'm using x, y as the input variables for f, and also as the input variables for g. In other words, what is going into g, which necessarily is what came out of f, is also what's going into f. So I'm confusing f's inputs and f's outputs, just like in the last problem. Right. So if I just write down the chain rule, and side note, this is kind of how we write down the chain rule. Namely, it's a product of derivative matrices. If I leave my variables confused, then it would suggest I just multiply those Jacobians and I get a wrong answer. But I can avoid that simply by being more careful about my choice of variables. Let me write a little quick diagram here. I've got this, whoops, let me make a better color here. Got a function f. I've got a function g. I have already decided that I want x and y to be the input variables for the f function. I need to give a name to what comes out. And arbitrarily, doesn't really matter, I'm going to call those outputs u and v. So what's coming out of the f function, I decided to call u and v. Because I'm composing these two functions, what comes out of the f function has to be what goes in to the g function. So that tells me I need to rewrite g, same function now, just in terms of these other dummy variables, u and v. I picked arbitrary. So you know this is the same g function, just written with respect to different variables. So there's our little diagram. This is our cheat sheet of what's a function of what and what equals what. Right? And so now, be as sloppy as you like, you can write the Jacobian product of the Jacobians. You compute those individual Jacobians. And there's no confusion of variables. There's a tip-off right here that that what is there has to be rewritten in terms of what it is. Now, how do you know what is U? Well, we assumed, we sort of chose U to be the first input to G, and therefore it's the first output of F. And therefore that goes there. Everybody see how that works? Okay. Likewise, V, what do I do with that V there? Well, V is the second input to G, therefore it's the second output from F, and therefore it's that, which goes there. Okay, so I just wanted to show you this example of how to avoid confusion of variables. It is a nasty little problem, really. Not only am I going to phrase questions to you sometimes like this, with my variables confused on purpose, right? See who's paying attention, right? But also, the problems will come at you in life sometimes like this, right? What variables, what dummy variables are used in describing a function might sometimes be arbitrary and a little awkward, and you have to be on the lookout for this. And if you're not on the lookout for it, then you're going to get it wrong at some point. So it's kind of part of what you have to do when you're using the chain rule. Okay, moving along. So I want to talk about second derivatives. Here's our single variable situation. If I have z as a function of y as a function of x, then here's our single variable chain rule. I guess you could say this is kind of a really simple special case where we have one intermediate variable between the input variable x and the final variable z. All right. This is a first derivative chain rule because it's a way of helping us compute a first derivative of a composition, and that's fine. What if we wanted a second derivative chain rule? Now, I bet you none of you all have ever seen a second derivative chain rule. I hadn't really before I started writing the book. And I only did it here as an excuse to talk about an idea that's going to be important when we try to do the chain rule, second derivatives involving the chain rule in a multivariable setting. So this is kind of a silly exercise, and I don't really expect anybody to memorize the result I'm about to derive here. But again, this is an excuse to use an idea. That's why we're doing it. Okay. So, right, now you'll notice here I'm rewriting the chain rule using this subscript notation. And we talked about this a few sections back, that the partial of y with respect to x, I can rewrite that as y sub x. Remember this notation? And likewise, partial of z with respect to y. Okay, so suppose that I want to compute the second derivative of z with respect to x. So I'm going to take an x derivative of the existing x derivative. And the problem is it's kind of unclear what that means and how I would do that and how do I sort of keep track of what's going on here. So the idea here, the way we resolve this issue is notice that we have arguably two new variables. Yx, I want to treat it as a variable, as a new sort of participant in our little study. And then likewise, zy, I'm going to treat that as a new variable. And my question is, where are those on the diagram? Where do they fit in this picture? What are they functions of? Is anything a function of them? How do these variables relate to our existing variables, and what relates to what directly? So it turns out to be a pretty straightforward answer. If you want to know what yx is, looking at yx, keep in mind that y is a function of x. Now what happens if you take a function of x, this is y, and take a derivative with respect to x? It's still a function of x. Right? So yx is going to fit in our diagram like so. It is another function of x. So is y. Y is still a function of x. That's not going anywhere, but now I have a new variable yx, also a function of x. Likewise, what is zy a function of? Well, z was a function of y. If you take a derivative with respect to y, you're still going to have a bunch of y's in there. And so it's a function of y. Zy, like z, is a function of y. So what I want to encourage you guys to do is consider that when you're using the chain rule, thinking about taking second derivatives, make yourself a little diagram like this, what I like to call a little road map. And consider that you might need to make reference to this from time to time. And here's where you're going to see where we're going to need to make reference of it. Keep in mind, here's what we're trying to do. Trying to compute a second partial. Well, it's not even a partial now. This is a single variable. So this is a second derivative. Trying to make a sort of a second derivative chain rule. So I want to take a derivative of what we already know by the chain rule is the derivative of z with respect to x. Product rule, right? That's just writing down the product rule. And now we're going to look at each of these objects in this formula one at a time and see what we can say about them. So let me start at the back. This one's actually pretty easy. If I have yx and I take the x partial, then that's the x partial of the x partial of y. That's just yxx. Second partial. No problem. There's no composition involved here, so that's you just write it down. Okay. Zy, fine. Leave that there. Gosh, I wish I had more colors. Or yx, I'm going to leave that there. So what I want to focus on now, though, is what is that? What is the x derivative of zy? How do I think about that? And here's where the diagram is going to answer our question. I've got zy, and I'm taking the derivative with respect to x. So that term there is the derivative of a composition. The two objects, the thing I'm taking the derivative of, the thing I'm taking its derivative with respect to, are separated by an intermediate variable. And so this derivative, this blue circle, partial of zy with respect to x, I can't just write it down immediately. I've got to use the chain rule. So that, by using the chain rule, turns into that. All right, you look at the two different arrows. The x partial, it's not partial, the x derivative of zy is the derivative of zy with respect to y times the derivative of y with respect to x. Now let me pause on that for a second. Does everybody see what happened? Everybody on board? Okay. Yeah. I'm sorry? Sure. Okay, so the point is that this term, this factor here that I'm interested in computing is a derivative of variables that are separated by an intermediate variable. There, right? Okay. And so that means that we have to use the chain rule. And the chain rule says that the derivative of a composition is just the product of the individual derivatives. And those individual derivatives are these. Yeah. Okay. Right, so, and then those simplify. The partial, I keep saying partial. Force of habit. The derivative of zy with respect to y, that's not a chain rule problem. That's just second derivative of z with respect to y. Partial of y, again, derivative of y with respect to x, that is just yx, which, by the way, is that, and so I get yx squared there. So altogether, here you go. Here's the sort of the punchline. The second derivative chain rule for single variable calculus would look like that. Again, never seen that before, a few years ago. And it's not that you're going to use this formula, and I'd encourage you not to memorize this formula, but the point here was to communicate the idea that when you're doing second derivatives and using the chain rule, a diagram like this will help you keep track of what goes where and relates to what by what, and therefore in what cases you have to use the chain rule, and in what cases you don't. Right? So we're going to use this idea now, same idea, to understand second derivatives in a multivariable situation. So this is the classic first example. The idea is I'm going to view x and y as functions of z. Sorry, I'm saying it backwards. Z is a function of x and y. So a simple multivariable function. And I want to ask, how would I understand the derivatives of z, first derivative, second derivative, various derivatives of z, if instead of thinking of z as functions of x and y, what if I wanted to think of z in polar coordinates? And keep in mind that in polar coordinates, x and y are functions of r and theta. So, side note, this kind of a calculation gets used an enormous amount in physics and engineering. And the reason why is very often that you have functions that are written in rectangular coordinates, but you need to know how to understand them in polar coordinates or in spherical coordinates. There's a sort of a spherical coordinates analog of this. And again, there's a pretty simple reason why you might want to do that, and that is the world's full of circles and the world is full of spheres. So, very common situation. Right. So, okay, fine. So let's write down a couple of partial derivatives now. I don't have to stop myself from saying that anymore. If I want to understand the partial of z with respect to r, then there you go. Chain rule. And again, what you have is two terms. There's the propagation of changes by way of the x variable, and then there's propagation of changes by way of the y variable. No big deal, just chain rule. Okay. And then notice that conveniently, a partial of x with respect to r, I know that's easy. X is r cosine theta, so that r partial is just cosine theta. And then likewise, the partial of y with respect to r is something I can write down as well. So get an easy formula here for partial of z with respect to r. Similarly, for partial of z with respect to theta, I'll let you guys fill in the blanks on that same basic idea. Okay, so what if we want to do a second derivative? I'm going to show you how to take the r partial of that already computed r partial. We're going to do the same idea that we did up here, which is to realize how the new participants in the algebra fit in on our diagram. So these new objects, what are they functions of, and therefore how do they sort of join up with the rest of the arrows? So, okay. Well, let's look at Zx. Where is Zx on this diagram? Well, don't forget, Z is a function of x and y. So imagine some expression involving x's and y's. Now what happens if you take this expression involving x's and y's and take a partial with respect to x? Well, it's still going to be an expression involving x's and y's. So Zx is a function of x and y. Is that cool? Everybody happy? Okay. And likewise, Zy is a function of x and y. And the arrows get kind of messy. I've redrawn this diagram down here, but there you go. So there's our new diagram. And as we go through and start taking derivatives and using the product rule and following the usual process, I just have to keep making reference to this diagram to keep track of, wait a second, what derivatives can I just write down, and what derivatives require me to use the chain rule. And if I do have to use the chain rule, then what are my intermediate variables, and therefore what terms do I have to write down? Okay. So this diagram is going to be our big friend here. So let's start off. Now keep in mind, I've already computed the partial of z with respect to r, and I'm taking the r partial of that partial of z with respect to r, which on the last page I computed to be this. Okay, so in some sense we start here. All right. Well, there's a lot to keep track of. When you're working one of these problems, don't get overwhelmed. Just go slowly and methodically and ask yourself one bit at a time, what's the first thing that I have to do? So the first step I'm going to make here is to note that this term involves using the product rule, and that's what the product rule looks like as applied to that term. And secondly, this term, got to use the product rule because it is a product, and applying the product rule to that gives you these two terms. So I haven't really done anything chain rule-y yet. I just wrote down the product rule and start off. Is everybody on board? Yeah.
What would happen if you move a step further?
If what?
If you move a step further.
I couldn't hear you. I'm sorry.
Go to the next equation. The next,
oh, where do we go from here? Oh, yeah, I'm about to do that.
Oh, okay.
Yeah, okay, yeah. Oh, yeah, I'm not done. We're not done yet. No, we've got several things left to do where we got to, make reference to this diagram. And yeah, lots to fill in yet. Okay. Yeah. So the first observation I want to make is that this term is 0. Now, the diagram is going to tell us why. The diagram observes that, well, theta, and therefore cosine theta, is over here. R, that I'm taking its partial derivative with respect to, is there, and theta is not a function of R. Right? In fact, when it says take a partial derivative with respect to R, let's take a moment and remember, what does that mean? Partial derivatives with respect to R says, look, you're going to view that as a variable. All of the other variables you're going to treat as constants. So the mere fact that it says partial with respect to R means you're going to view theta as a constant. And if you're viewing theta as a constant, what is the derivative of this function of theta? That's a function of a constant. It's a constant. So its derivative is 0. All right, so that term is 0, and likewise, that term is 0. Everybody good? Right. Okay, so all I have left then is this term and that term. Fine. Okay. What do I do with this guy here? Let me zoom out a notch. Oh, out, not in. Sorry. So looking back at our diagram, Zx is there. R, that I'm taking its derivative with respect to, is there. So there is a chain rule issue here. Zx is not directly a function of R. Zx is a function of intermediate variables that are functions of R. So think about the different paths by which R changes would propagate to Zx changes, and you have two such paths. The intermediate variables are x and y. And that gives you that term along the x path and this term along the y path. Everybody good? So you got to look carefully, think through. I mean, along this purple path, for example, we're going to take the partial of Zx with respect to x and multiply by the partial of x with respect to R, and that's exactly what I've got. Likewise for the orange path. Okay. Ditto over here, looking at this. Ends up being that. ZY is there. R is there. Again, there are two paths. There's that yellow path that gives you this term, and there's this blue path that gives you that term. All right. And then it's just a matter of sort of simplifying, rewriting, collecting terms, etc. Partial of zx with respect to x, that's just zxx. Right? Partial of x with respect to r, again, we already know what x is as a function of r. That's just cosine theta, etc., etc. Don't forget, don't make any inadvertent recopying, transcription errors. Make sure that you carry down all of your factors. There's a lot of stuff on the page, so spread out. Give yourself plenty of room. Don't try to fit it all onto one teeny tiny little line of college ruled notebook paper, right? Take 3-4 lines. Take plenty of space, plenty of room. Use big parentheses, different kinds of brackets to help you remember where those groupings are. And take plenty of space and write neatly to help you keep from losing your mind. I had a friend in college who not only did he do these things, but just to give himself more room, instead of using the paper like this, he turned the paper that way. And that gives you significantly more room to write bigger and therefore spread wider as you write across the page. So, if you need that, it might be useful. Okay, so that finishes the chain rule. We'll move on to the next section. Talk about implicit differentiation. I think a lot of y'all have seen implicit differentiation before. Let me start with what I feel like you've probably seen, and then I'm going to complain about it. So here's what you've probably seen before. Let's suppose that you're given this is the equation of a circle of radius 5 centered at the origin. And if the question is, how do you find the slope of the tangent line at the particular point 3, 4, then, correct me if I'm wrong, hopefully you've already seen this, you just do what we call implicit differentiation. Take the derivative of the whole equation with respect to x. Derivative of x squared is 2x. The derivative of y squared, well, now, okay, slow down. The derivative of y squared is not just 2y. We're taking the derivative with respect to x. Y squared is a function of y, and y is a function of x. And so using the chain rule, you get 2y, y prime. Right? I hope that looks familiar. Everybody, it's a standard single variable calculus move. Derivative of constant is 0, of course. We wanted to find the slope of the tangent line. That's y prime. So you solve for y prime. You get that function. I want to know what that slope is at this particular point. So I take that point, plug it into there, and that gives me that answer. So I hope that looks familiar. Now let me complain. In this problem, we made an assumption that is not obvious. In fact, which is often false. And that's not good, right? That's a problem. So here's the assumption we made. I just assumed, you might not have even heard me say it, that y is in fact a function of x, thus allowing me to do this. I can't just say y is a function of x. It certainly wasn't given as a function of x. That's not saying y is a function of x. That's saying there's some other thing that's a function of both x and y. How do I know I can just assert that y is a function of x? Well, okay, so you can look back at, and by the way, here's a sort of an expanded version of what I just did there. See that in the process of computing that derivative, I am assuming that y is a function of x. So, sure, I mean, in this case, you can look at the picture and say that here's our picture, there's what our curve looks like, and there's the point where I want to compute the derivative, and Well, sadly, I must admit, y is not a function of x. Look at this. Fails the vertical line test. That's a problem, right? But this is an easily fixed problem. We just say, look, yeah, okay, sure. But all I really want to know is the slope of the tangent line. So I could say I'm not actually interested in the whole circle. I'm just interested in that part of the circle. And I can throw away the rest of the circle. Let's just pretend that's not there. It's gone. It's not part of my curve. All I'm interested in is this little green curve. And on that green curve, y is very happily a function of x, no problem. Okay. In this particular case, yes. For that curve, that point, locally, yes, y is a function of x. But the problem is we didn't know it as we did the algebra. That the curve we were given happens to be a circle and something that we know a little bit about. It was a lucky break. What if this was a much more complicated equation, where I didn't know what the curve looked like? You can't just go out and assume that y is a function of x, because here's what you'd be afraid of. Here's the problem. What if your curve, not a circle, what if your curve looks like that? We have no idea what it really looks like, and I'm asked to compute the slope of the tangent line at that point. Well, I can throw away most of the curve, restrict my attention just to that part of the curve, but the thing is no matter, given where that point is, no matter how little of the curve I look at, I am failing the vertical line test. It's not a function. Right? Y, for this curve at that point, y is not a function of x. And not in some sort of just annoying sort of like formality kind of way. It really isn't. So in particular then, if on a problem such as that sort, if I were to write this down, y of x, that is garbage. It is meaningless, nonsensical garbage. Does that make sense? Everybody see the problem? Okay. All right. It's an issue. So in order to fix this, I'm going to study this scenario that we're worried about and try to get a way of algebraically, no intuition required, an algebraic test that I can plug in, and if it works, I would like to be able to draw the conclusion that, look, everything's fine, y is a function of x, and I can proceed with the old high school implicit differentiation that we would like to be able to do. Here's how the reasoning goes. Here's what the problem was. The problem is when we're at a point where the curve tucks under itself. I wanted to be on. Let's do this. Thus making us fail the vertical line test. Right? If you're at a point where the curve does not tuck under itself, if the curve looks like this, then you just erase most of the rest of the curve and you're fine. And you pass the vertical line test, everything's fine, no problem, y is a function of x, go about your business. So the problem is when the curve tucks under itself. What is it that allows the curve to tuck under itself? I assert that if at the point in question, if the curve is in the process of at that point tucking under itself, it necessarily must have a vertical tangent line. Now, some students would raise their hands and complain and say, wait a minute, vertical tangent line, can you even talk about a vertical tangent line? We don't even know if y is a function of x. I didn't say anything about y being a function of x. It's no problem. That's a curve. That curve's a level set. Described by an equation. There's no issue with is something a function here. So that might have a vertical tangent line. Sure. No issue. So I would like to know, is there some way that I can identify when a curve has a vertical tangent line? Yeah, absolutely. There sure is. If a curve has a vertical tangent line, keep in mind the gradient is always perpendicular to the level set the equation, all equations can be viewed as level sets. Right? So the curve in question, write it as a level set, look at the gradient of that corresponding function, and see, is the gradient vector horizontal? If the gradient vector is horizontal, then we have a vertical tangent line, which means the curve might be in the process of tucking under itself, and we might be in the middle of a very nasty problem. Whereas, on the other hand, if I'm here, that's what the gradient would look like. If the gradient is not horizontal, then the tangent line is not vertical, and the curve at that point simply is not in the process of tucking under itself, and there's just nothing to be afraid of. Just erase most of the curve. Vertical line test passes, everybody wins, no problem. Okay. So, what we've gotten it down to then is this possibility here of a gradient vector that is horizontal. And keep in mind what the formula for the gradient vector is. The gradient vector is partial of f with respect to x, partial of f with respect to y. There's your gradient vector. Horizontal would mean that its second component is 0. So that partial derivative, the partial of capital F, the function whose level set you're looking at, that partial with respect to y tells the story. If that's 0, you might have a problem. You can't just say y is a function of x. If it's not 0, then that's not horizontal. Tangent line is not vertical. You have no problem. And implicit differentiate all you want. So this is called the implicit function theorem. This is a sloppy motivation. This is not a rigorous argument that I've made here. Yeah?
So if the partial with respect to y is 0, then you can't do this?
If the partial with respect to y is 0, then you don't know. It means that you have a vertical tangent line, and technically it could be that the curve is in the middle of doing an inflection point, in which case you technically actually don't have a problem. You just don't know, right? And when you don't know whether you do or don't have a problem, then you've got a problem. You see what I'm saying? So yeah, if it's 0, you can't proceed. Right, so here's what the implicit function theorem says. It's really just kind of a summary of what we were just talking about. Suppose I have an equation. Note I've written the equation as a level set of a certain function. So this function, in the case of the circle that we started with, this function is x squared plus y squared. Or x squared plus y squared minus 25, whatever. If you look at the partial of f with respect to y at the point in question that you're worried about, if that partial with respect to y is non-zero, then you're good to go. Y can be thought of as a function of x, and you can implicit differentiate as you wish. So here's an application of this idea. It's just an immediate application of the theorem. This is that same question that we did in a sort of a high school sort of approach at the start of this section. Looking at that curve. I want to find the slope of the tangent line, blah, blah. Note, I'm not going to dive into the implicit differentiation. The first thing I'm going to do is worry about the possibility that y might be a function of x. If I want to know dy dx, I need to know y is a function of x. So the way we decide whether y is a function of x, I look at the partial with respect to y, confirm that it's not 0. I'm going to take this x squared plus y squared minus 25. That's capital F. Take its partial with respect to y. It's 2y. At the point in question, that's equal to 8. It doesn't really matter that it's 8. What's important is that it is not 0. And then I get to conclude, as I was hoping, that y is locally a function of x, so I can treat y as a function of x and then do exactly what I would have done in a high school calculus class, and it's fine. So there's 2 steps in these problems. It's very important to treat these as 2-step problems. Step 1, you have to apply the implicit function theorem. You have to confirm that y is a function of x before you start treating it as a function of x. You take one partial derivative, see if it's 0 or not 0. It's not that hard to do. You just take that one partial derivative, see what it is. Having done that, then you know that what you're writing down is not garbage. Yes?
So if it's 0, then there's no idea.
If it's 0, then yeah, you've got a problem. You don't know if y is or isn't a function of x, and so I was observing to Arturo. If you don't know whether you have a problem, you have a problem. Right, it's a different kind of a problem. But so you can't, certainly if you get 0, you can't just do this, right? And you would have to some way or another try to make some other argument to assert that y is a function of x. Yeah, right. Okay. All right, so now this is a single variable calculus thing. Arguably, it's a little bit multivariable in that this function here is a function of 2 variables, right? We're taking a partial derivative of it in order to draw our conclusion. It's kind of multivariable. But nevertheless, ultimately, we're drawing the conclusion that we have a single variable, ultimately a single variable problem that we can address with single variable derivatives. And this gets done in single variable calculus classes. So I want to show you now a multivariable version of this. And the multivariable implicit function theorem considers this scenario, where it's not just f of x comma y equals some constant. In other words, it's not just an equation of 2 variables. Suppose it's an equation of more, possibly several variables, at least 3. Okay. So I'm going to draw a picture. I didn't give myself any space here in the book, so let me give myself a new page. Yeah. So if you have, whoops. Let's see here. You have f of x, y, z equals a constant or 0 or whatever, doesn't really matter. Well, we've got a surface, right? And I'm going to draw a surface where there's the potential for a problem. So that's my attempt to draw this. All right? Okay. So it's a surface that wraps under itself. Now, if I wanted to, find, let's say, at some point on here, maybe at that point there, if I wanted to know, at that point, what is the partial of z with respect to, that looks like a minus sign, doesn't it? Partial of z with respect to x is really not a problem. I could throw away most of the rest of the surface, look just sort of nearby. There's nothing wrapping under itself. We pass the vertical line. Sorry, wrong color. We pass the vertical line test, no issue, and everything's fine. There's just no problem. Go ahead. Right? The issue is I can't know for sure that that's the point that I'm looking at. What if the point is a point like that, where there's a vertical tangent plane, and therefore the possibility that maybe even locally the surface is kind of wrapping under itself. In other words, how do I know I'm not at that point right there? Right? And then throwing away the surface, throwing away most of the surface is not an option. You can't throw enough away, and z at a point like that simply is not a function of x, and you absolutely cannot do that. So again, how do you tell the difference? Well, there's similar argument. And the argument goes like this. What we're interested in, what we're worried about, is points where the surface wraps under itself. If it wraps under itself at that point, then there is a vertical tangent plane. Keep in mind that this is a level set, and so its gradient vector is perpendicular to that tangent plane. So if the tangent plane is vertical, then the gradient vector, being perpendicular, must be horizontal. Let's look at what that gradient vector is. It's partial of f with respect to x, partial of f with respect to y, partial of f with respect to z. A horizontal gradient vector would mean that that third component would be 0. So there's your worry. Right? You're worried about the possibility that that might be 0. If that's 0, you've got a horizontal gradient vector, you've got a vertical tangent plane, you might have a wrap under problem, and this might be the question at hand of what is the partial of z with respect to something might be nonsensical. Right. On the other hand, if this partial derivative is not 0, then that means that your gradient vector is not horizontal. It's got a vertical component, which means that the tangent plane would be not vertical, and nothing's wrapping under anything. Again, everything's fine. Go ahead. So that's the punchline of our multivariable implicit function theorem. Whichever variable you want to view as a function of the others, take the partial of that, the partial of f with respect to that variable, and confirm that it's not 0. And then the variable you want to treat as a function, you can treat as a function. Now, in the problem that we just looked at, it was z. I was wanting to compute partial of z with respect to, I don't know, let's say x. Can I view z as a function? Z is what I want to take a partial of, so z is what I need to worry about might be a function. Take a partial with respect to z. And hope you don't get 0. Okay. Right, so here's an example. Yeah, we're doing just fine on time. Let's look at this equation here. That's an equation involving 3 variables, so this is some surface in R3. You can probably speculate on what this thing might kind of sort of look like. By the way, it's kind of sort of sphere-like, except it's lumpy and weird because those aren't squares, right? But they're even powers, and so we expect this to look kind of like a sphere, sort of a lumpy sphere. I am going to look at that point, and at that point, I want to know this. Which is partial of z with respect to x, hopefully. Right, slope of a certain tangent line, perpendicular to the y-axis, which means in the x direction, so partial z with respect to x. So now, that's the question. This is what I would like to compute, partial of z with respect to x, but worry, how do I know z actually is a function of x? Again, it's not given as such. In fact, I can't solve for z as a function of x and y here, because I'd have to take a 6th root, and that gives multiple values, and there's a definite worry that this is not a function. How do we decide? Well, the way we decide here is, let me zoom in a notch to make this easier to see. I want to know if z can be viewed as a function of x and y. That's the variable that I want to view as a function, because that's the variable I want to take a partial of. So I need to take the partial of f with respect to that variable and hope I don't get 0. So fine. Here's our function. That's the function whose level set we're looking at. there's its partial with respect to z. Plugging in the point that we're interested in, plugging in x equals 1, y equals 1, z equals 1, and look at that, it's not 0. So having computed this partial, having gotten not 0 as our answer, I conclude by the implicit function theorem that, yeah, z is a function of x and y, and you can totally just proceed and compute the partial derivative you're interested in, and don't worry about any nasty problems because none are going to come up. Okay. All right, so now the algebra is the last interesting thing we need to talk about. How do you actually compute that? So keep in mind what we started with here is that f was a function of x, y, and z. I now have a new picture. My new picture is that z is a function of x and y. So this is my little roadmap. This is my chart of what's a function of what. And now let's take the derivative. The original equation, you'll recall, was x squared plus y to the 4th plus z to the 6th equals 3. And we're going to take a partial with respect to x of that equation. Okay, now, be very careful. Keep in mind your roadmap. Partial of x squared with respect to x, fine, 2x, no problem. That's the easy one. What's the partial of y to the 4th with respect to x? Well, keep in mind, y is not a function of x. Right, so your roadmap is telling you what to do here. Said differently, when you're taking an x partial, if you're viewing z as a function of x and y, x partial means hold y constant. So you're taking the derivative of a constant, and that derivative is 0. Most common mistake I see students make in this situation is to put 4y cubed. Or maybe 4y cubed partial y with respect to x. Doesn't make any sense. Not viewing y as a function of x. It's not a chain rule problem. It's just 0. Make sense to everybody? Okay. Z is a function of x, among other things. So in taking its x partial, I do use the chain rule. That gives me that. Right? And having done this, now I have a resulting equation. I can solve for what I'm interested in. I wanted to know the partial of z with respect to x, and I get this formula. Plug in the value, x, y, z, that I'm interested in, and there's your answer. Everybody happy? All right. Okay. So now we've only got a couple minutes left. Oh, yeah, go ahead.
Yeah, could you have taken partial with respect to y?
Yeah, it would have been a different question. Yeah, I mean, in this question, the question was to compute the slope of the tangent line, cross-section, blah, blah, a certain particular plane. And the plane was perpendicular to the y-axis, and that's why I did an x partial, right? But yeah, if the question had been blah, 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 perpendicular to the x-axis, then I would have wanted to compute the partial with respect to y. It would still be that it would be z that I would be wanting the partial of. So I would still be doing the partial with respect to z to check that it is indeed a function. So the first part of the problem wouldn't change. But then down here, yeah, I'd be taking the derivative with respect to y. X would be the constant. Then this y term would have stuff in it. Yeah, etc. Obviously. One thing else to be aware of is you've got to look out. There will be some situations, actually, in fact, most situations, you're going to have terms where in the differentiation you have a product rule come up. So be on the lookout for the product rule, having multiple factors. Yeah.
What would be the difference between solving the partial of z respect to x and the partial of x respect to z?
So yeah, right. Well, if you want to take the partial of x with respect to z, I'll write this down.
What would that be perpendicular
Well, at this point, the sort of the geometric language would be awkward, right? But the problem might very well say, what is this partial? Right? And if it says, what is this partial, then your job is to note that that means I want to view x as a function. So it would be down here, I'd be taking the partial with respect to x. That would be x, because x is what I want to know if, hopefully, presumably, I can view as a function. Again, fingers crossed, hope I don't get 0. And then once you know that it is, then you'd take your original equation and take a z partial of that original equation with the understanding that now x is a function of y and z. Okay, so we're out of time. We'll call it a day here. A nice stopping point. We just finished. Let me say one other quick thing very, very quickly. I'm going to be momentarily skipping the last 3 sections. You'll note this on the lecture schedule. 411, 412, 413. We're not going to do those now. We're going to do those at the very end of the course. I'll explain why at some point. But so the very next thing we're going to do is go on to Chapter 5. Okay, see y'all later.